Right, the point about molecular geometry is here. Imagine that the nucleus of the central atom in a molecule is placed at the center of a sphere, much like the yellow ball we've just been looking at. Now you place the electron pairs on the surface of the sphere, just as we did, so that they're as far apart as possible. Okay, that means they all have the same amount of repulsion, equiangular we spoke about. Now the resulting geometries are very simple. If you've got two pairs, very clearly, if they're as far apart as they can be, then it's going to be linear.
Yeah.
And we'll see, I'll show some pictures in a moment. Three pairs, trigonal planar. Oh, we're getting into some serious terminology here. 4, tetrahedral. That name should be fairly familiar. 5, a trigonal bipyramidal. And 6, octahedral. Right, let's move on. Now, here is a picture of the linear arrangement. Here's our sphere. Here is the nucleus. And if we put two pairs, and those dots represent the pairs, and we place them on the surface of the sphere, you can see that they're going to be as far apart. And if we have another atom connected here, sharing that pair, and another one there, that's what we would expect with water. But with water, we found we had 4 pairs. So we've got to look for a different shape. Now, trigonal, that just means 3 angles, as in trigonometry. 1, 2, 3. 3 pairs, there they are. That's how they are shared. Here is the one with 4, and you can see that these angles are all the same.
That's the
tetrahedron. Okay, that would be the shape of the molecule or of the crystal structure in diamonds. Very, very strong. Tetrahedral is 4.
So our CH4, the methane molecule,
there,
have
same,
that shape.
See, and it would be just in that shape. Then if you've got 5 pairs, they look like this. 1, 2, 3 on a plane, and then 1 above and 1 below. Right, now this is called the octahedral shape. You see we've got 1, 2, 3, 4, 5, 6 electron pairs. 6 pairs, and yet it's called octa. We know that means 8. And here's the trick. If you look at 1, 2, 3, there is a face there.
Yes.
There is another face at the back. There's one on the side, and there's one over here. That top part will give us 4 faces.
And the bottom one gives us 4.
Another 4, 8 faces. Tetrahedral, 4 faces, even though there are only 6 pairs.
But we've got 8 faces.
8 faces. There we have the different kinds of molecular geometries that you can get. Now, clearly, water is not octahedral, I beg your pardon? Tetrahedral.
It's tetrahedral.
Water is tetrahedral. It's got 4 faces. It's got 4 pairs of electrons. Now, let's have a look and see what this actually means. Now, if water is octahedral in shape, there's our oxygen. Here is a hydrogen. And here is another hydrogen. That, by the way, is
the bond angle.
109 degrees. 109 degrees. But now it's tetrahedral. What we haven't got in here, remember there's an electron pair, electron pair shared, 1 from the hydrogen, 1 from the oxygen. But there are those 2 pairs of electrons that we haven't spoken about yet.
Yes.
And you know what? They're sitting up here. One sits over there, and another one comes out the other side here. That's how we draw it, to show that they're going up. So in other words, we've got 1, 2, 3, 4 pairs of electrons. There are 8 electrons. They are distributed in an octahedral shape. Now, if we look at this carefully, we can make other predictions or deductions from the shape of the molecule. For a start, let's remember that the electronegativity of hydrogen is 2.1. And of oxygen is 3.5. The difference here, 1.4. That's a pretty big difference. You know what it tells us about these two electrons?
It tells us that the two electrons in the oxygen-hydrogen bond are more attracted towards the oxygen atom.
Okay, they're going to spend a bit more of their time.
The hydrogen atom.
They're going to spend a bit of their time up there.
Yes.
The other thing is, all right, here this is strip the electrons away from the hydrogen.
So the hydrogen atoms become slightly positive.
So this side is going to be slightly positive. What about here?
There we've got that set of electron pairs. They are negatively charged, so that part of the molecule is slightly negative.
And it's been contributed to by the movement of these electrons up this way. And so that looks slightly negative.
Yes.
So in fact, what we get here is an oxygen hydrogen molecule with a positive end and a negative end. So it looks like a little bar with a positive and a negative. Now, what kind of deductions can we get from this? It seems to us that the molecule of water is polar.
It's polar, but in fact, we would say that it is dipolar.
Yes.
And in that case, we are also catering for the fact that those two parts are not completely negative and positive. In other words, it's a slight
separation
of charge that is existing, and that makes water to be a dipole molecule.
Does this mean, Tiniko, that if we bring a charged body near water, that the water reacts in some way, is perhaps attracted?
Exactly. Exactly.
Does it happen, or is that just a prediction we make?
It does happen. It does happen when we do the electrolysis of water as well. It does happen when we bring something charged towards water molecules. There would be something that will happen there to show that there is either a repulsion of a repulsive force between like charges and attractive force between unlike charges, because water is a dipole molecule.
How can we show that?
I think what we could do is to maybe charge a particular object, like a piece of plastic, and bring it
near a glass of
water or something, and let's see what happens.
Okay, let's have a bit of fun and see if this prediction that we've just made using VSEPR about the shape of the water molecule is going to have some practical outcome.
Yeah.
Watch here.